I'm Evelyn. I'm a PhD candidate at the University of Toronto, and I'd like to talk about some simulation work that I've been doing with my collaborators there, funded by NSERC. So I work on M-Earths, which, for the purposes of this talk, I'm defining as roughly Earth-sized rocky planets in the habitable zone of an M-dwarf star. And so because the star is small, the planet is close to the star, so we assume it's tidally locked. So this diagram over here just kind of shows what that looks like. So we have the star somewhere over here, light from the star hitting the planet at the substellar point, which is always at the same place because the planet has a permanent day and night side. And the terminator is kind of a cool word for the dividing line between the day side and the night side. So just kind of keep that in mind. I'll be using some of these terms. Now, the base assumption is that these planets have what we call an eyeball climate. So again, we have the star here. The assumption is that the night side is frozen and part of the day side is unfrozen near the substellar point where it receives the most radiation. And you would assume that's a circle. This is actually an oversimplification, but it's kind of a good starting point. So I have a few questions that I'd like to be trying to answer today. First of all, how does land configuration affect M-Earth climates? How does the mass of the atmosphere affect their climates? I'll be answering those using a 3D GCM general circulation model called exoplasm. And then the next part is, can we tell these climates apart in observations? I'll be using a radiative transfer model based on my exoplasm simulations to look into that. So to start, I'd like to talk about land configuration. So if you recall the eyeball climate, we kind of have a cartoon of this here. The idea is what happens if we put land in that warm, deglaciated region, because that's the region that's probably the most interesting. But what's going on the surface there should have a climate effect, presumably. So I've done this in a systematic way, as I'm showing over here. Basically, we have two opposite continent configurations where either all of the land is in a circle at the substellar point, so that's the substellar continent over here, with ocean everywhere else, and if the ocean is cold, there's ice instead of open water. And then the opposite, substellar ocean, putting land everywhere except for a circle at the substellar point where there's water. And we vary the size of the circle in all of these simulations, going from 0 to 100%. So here you can see that sometimes there's ice-free ocean and sometimes there's not. And these ones, there's always some ice-free ocean because of where the water is. So now what happens to the climate when we run the climate model with these? There's a lot going on here, so let's just take it slowly. On the left here, we have substellar continent models with different land fractions. So this first column is the land map, just looking straight down at the center of the day side with the night side not shown. And the second column here shows the precipitation and evaporation. So red is evaporation, blue is precipitation. You'll notice it always rains at the substellar point and water evaporates from the ocean everywhere else on the day side. And this is true for these substellar ocean models as well. You get clouds and precipitation in the middle of the day side and over ocean, regardless of where the land is. So the water comes toward the center of the planet where it's warmest, rises, it condenses out, and you get rain. So we also get kind of a range of temperatures depending on how much land there is, with high land fraction planets having hot and dry day sides, which is what's shown in this column here. So these are some pretty significant climate differences, like on a spatially resolved level. This is what this looks like globally. On the x-axis, we have day-side land fraction, so the size of the circle for these two land map types. And on the y-axis, we have temperature on the left and water vapor on the right. You'll notice that there's the largest discrepancy between the two at partial day-side land cover. So when it's not an aquaplanet or a land planet, somewhere in between, it really matters a lot where the land is, because that influences the amount of ice-free ocean that's available on the planet for evaporation and putting moisture into the atmosphere. And these curves kind of follow each other. So this is already a climate uncertainty that we need to kind of think about. Now let's make it more complicated by changing another parameter, the mass of the atmosphere. So like land configuration, that's not necessarily something we can know about a planet in advance. So I varied it in my simulations. The idea is basically make the atmosphere thicker or smaller. That's what I've tried to show over here. And these are the same curves that were on the previous slide, but this time for a range of pressures. So increasing the amount of N2 in the atmosphere. And again, you get the same land fraction and land configuration dependence, but in addition to that, the curves are shifted up or down depending on the pressure. So they overlap. It's very confusing. There's clearly some climate effects here that need to be paid attention to. And so then the next thing we want to know is, can we ever know this stuff? Can we tell these apart in observations? So the way these planets will be observed is with transit spectroscopy, which is what JWST will do. I have a kind of image of what that looks like. Basically, when the planet passes between the observer and the star, it blocks out some of the star's light, which is measurable. And there's a wavelength-dependent contribution to the amount of light blocked, depending on the molecules in the atmosphere and where they scatter and absorb. So based on what wavelengths block the most light, we can tell what's in the atmosphere. This is really hard to do for small planets, but this is like the theory of it. So the question then, because most of the water, if you'll recall, was at the substellar point, is how much water is making it to the terminator, because the terminator, the terminator is where we're getting the photons from. We can't directly image the substellar point, so we're getting the light passing through the terminator. So I have some profiles here of specific humidity for the two different types of land map. This is just all at the same pressure. Basically, we have pressures, so going upward in the atmosphere on the y-axis, and specific humidity on the x-axis for near the substellar point and near the terminator. So looking for a relationship between the amount of water in the rainy zone and the amount of water we can see. Substellar ocean models all look pretty much the same, which makes sense. There's water there. There's a bit less at the terminator, but it's still there. For the substellar continent models, the ones with a lot of land have much less water at the terminator, but still some. So maybe we can tell the difference. So now I'd like to show some synthetic transit spectra I've made using only water. So I've ignored all other possible things that could contribute to this. So on the x-axis, we have wavelength that the instrument is observing at. And on the y-axis, we have what I've defined as amplitude. So basically the difference between the transit depth that you get, so the amount of light blocked from the star, and the minimum amount. So either the amount just by the rocky planet itself, or the lowest cloud deck, or the lowest part that would be visible. Because it's really this difference that we're looking to measure, more so than the actual size of the planet itself. So these are just for a few selected simulations from my parameter space. And so varying only the land and the pressure, we get quite a sizable difference in these water vapor spectral features. So these are kind of a range of what a specific planet might produce. And then on the bottom, we have the cloudy version. So these same ones, but with clouds included in the radiative transfer. And you'll notice that the features are smaller, but also they're not all affected the same way, depending on where, like how many clouds are at the terminator, which varies depending on different factors. So it's a bit confusing. I'd like to just focus on this feature though. So I'd like to show basically the top of this feature for a variety of models. And that's what this looks like. On the left, we have the cloud-free version. On the right, we have with clouds included. Again, these curves kind of follow the same shape as the temperature and water vapor from a few slides ago. But when you add clouds, it gets a lot worse, unfortunately. Basically, there's like some correlations in the cloud-free version. These high-pressure, low-land models have much taller spectral features, so you might be able to detect that or tell the difference. But then when we add clouds, what happens is that these models with the most water vapor are also the cloudiest at the terminator, and consequently, the effect of clouds on the spectrum is much higher. So, it gets like artificially subdued. So it looks like these dry models over here have the most water, but that's not actually true. So observing this, it's going to be very hard to tell what's going on the surface of the planet. Just try to end on a happy note. There's a huge range of climates here. We can't necessarily tell them apart, but a lot of them could be habitable, and we might be able to detect water in some of them. So, I'm still cautiously optimistic, I guess, but it's more important, I think, to account for the fact that there are these unknowns instead of just trying to make assumptions about what's going on the surface of the planet based on its transit spectrum. I'll stop here, and I'm happy to take any questions.
Hi, great talk. Really interesting stuff. So I'm wondering about, you have these simulated transit spectra, and it looks a little pessimistic based on how close those lines are, but JWST has been delivering some exquisitely precise spectra. So I'm wondering if you have plans to model the noise properties and stuff, and actually simulate JWST observations of these kind of things to see if you can actually distinguish maybe a few things, because the transit spectra are so precise because of this incredible instrument that we have.
Yeah, it would be good to add some instrumental noise to them. It's also really hard to do that accurately. It's harder to get precise spectra for these smaller stars. Most of what's been coming so far smaller planets. Bigger planets are easier to get good data from. But yeah, there's more photon noise in the far or mid-infrared compared to the near-infrared, so I think it'd be good to focus on that. But yeah, it would be it might be possible to tell some of them apart, but it would be a good thing to look into. Thanks for the question.
Taylor Plattner at Georgia Tech. Great talk. Also, just wanted to say all the other talks were very interesting this morning and super cool. I used to do exoplanet stuff when I was an undergrad, so you're taking me back to, I guess, my old days. Sounds like I'm an old person. But I had a question on, I know you're doing simulations, but are you going to eventually look at specific planets? And if so, do you have I don't know, there's kind of I used to do this development of a prototype instrument to put on ground-based telescope to vet out interesting planets. So I didn't know if you had I don't know, anything to vet out interesting planets to you, with JWST or with any other telescope. Sorry if that's a terrible question, but just curious.
No, it's an interesting point. I'm not an observer. I'm mostly just waiting excitedly for other people to get data. I would say the one I'm most excited about is probably TRAPPIST-1e, but excited and apprehensive at the same time, because it'll be really sad if they don't find an atmosphere on it. But yeah, ground-based observations would be another good way to look at these planets, because you can get such a bigger telescope.
Okay, yeah. Just with JWST, how often is it looking at if you had some planet that you're really interested in, how often is it looking at that planet? Or would you I don't know, I know TESS was another one that people were really excited about, so I didn't know if that was easier to get data to see that same planet more. Yeah. And I know like you were saying, it's not as great. Everybody loves JWST for a reason.
Yeah, well, TESS is a planet finder, so it's found a bunch of candidates. So anything that starts with TOI, TESS object of interest is what they're called. And then JWST is kind of needed, or it's like some large telescope is needed for follow-up to actually characterize their atmospheres, because it's much easier to find the planets than to see what's in their atmospheres, especially with such thin ones. Did that answer the question?
Yeah, Good talk, thank you.
Thank you so much.
Okay, we have time for one quick question.
Hi, that was also super. I'm pretty far removed from this exoplanet stuff. This is sick. So I have a question that I apologize for my inability to ask a more specific question about your work. That's just a lack of my understanding. But I'm curious that they were talking about how like this exquisite precision with JWST and all this stuff. And so how far off? Well, I'll preface by saying the past couple of decades, as I'm sure you're aware, our understanding of planetary habitability has really shifted with our increased understanding of these icy moons in our solar system and things like that. How far off is our ability to examine moons of exoplanets, given like a small enough star or something like that? Or is that just like so far off from reality, given our technological abilities at the moment?
I would say it's far off.
Unfortunately.
Like, yeah, the problem is that you have to like detect the planet and then the moon going around the planet, and they're just really hard to find, and they'll be even harder to observe, which is unfortunate because I bet exomoons are really cool. And that would also deal with the tidal locking problem. Like if an exomoon was orbiting its tidally locked planet, the moon will not be tidally locked to the star, so it could have day-night cycles, but they're just really hard to observe. But yeah, thanks for that. That would be really cool. All right.
Thank you for the talk, Evelyn.
Well, thank you.